a cognitive zoologist, and I'm going to talk about intelligent birds today, and therefore I thought I'd better introduce you to one right away. This is Dohli. She is a jackdaw and belongs to the corvids, the crow family. That's one of the two bird families, with the largest brains relative to their body. Dohli, bleib bei mir. Ja. Maybe you can't imagine that this little head has the brain capacity like that of a great ape. And to many people, and another reason why I brought her, I have to say, because I wanted her to be the first corvid in a TED talk. There has been a parrot before, and I thought it's about time for a corvid as well. If she now doesn't come back to me, then don't worry, then I'll pick her up in the break. But don't worry, she's not dangerous, because as you see, Dohli, she will find a place to sit, and then I'll pick her up later. Just do me the favor and keep the doors closed. So, so to many, crows don't have the most positive image, but why that is, I never understood. I find them highly fascinating birds, and I'm intrigued by their complex social life. And in fact, Dohli was brought to me when she was a chick, because she had fallen out of the nest prematurely, and I hand-reared her, and that established a very special bond between us. And this bond still lasts, although she's paired for many years with a jackdaw male. The ability to form bonds is very typical of jackdaws and of corvids. They form long-term friendships and lifelong pair bonds. They recognize former group members for many years, and they're virtually inseparable from their partner and are very tender towards each other. But the most fascinating thing about crows is their intelligence. And talking about jackdaws, they're, for example, extremely sensitive to eye orientation, and they recognize attentional states, even if it's a person and not a bird. They also use it they use eye orientation as communicative signals, but they also, in competitive situations, reason about the perspective of others and consider their knowledge states. So they show aspects of a theory, so-called theory of mind, that's something that develops in human children quite late. So the past decades have seen a major increase in research on the animal mind. And until the 90s, these studies largely focused on primates, our closest relatives, and they revealed that they exhibit many cognitive abilities that have originally considered to be uniquely human. And that's not so surprising, considering that our last ancestor lived only 6 million years ago and that we share the majority of our genome. But throughout the last 15 years, it has been shown that crows and also parrots parallel the great apes in cognitive ability. This was of major significance. And the implication of it is that intelligence not just evolved in our lineage, but several times independently. And interestingly, this is also matched if you look at brain size in the vertebrates. In addition to our lineage, the primates, there's 3 more groups that stand out for their large relative brains in relation to their body. And very surprisingly, this includes 2 bird groups, crows and parrots. And I mean, their last shared ancestor with us lived around 300 million years ago. So this is amazing, and it shows that studying corvids and parrots they might be very good candidates for studying the evolution of complex cognition. To many, this is boring because some people still want to draw a clear-cut line between animals and humans. I mean, we are certainly very, very special, but we are still a primate species and we have an evolutionary past. As a cognitive scientist, I find it hugely fascinating to trying to understand how and why we became so special and why our brain expanded not so very long ago all of a sudden and became enormously big. We have the largest brain relative to body size of all animals. And we are very special because we are by far the most innovative being on the planet, and we can realize what is otherwise merely potential, but foremost we can recognize potential and we can dream up theoretical possibilities. Dohli, yeah, come here. We can dream up theoretical possibilities and it's slightly distracting for me because she's now calling for me. Dohli? But so we humans have the ability to dream up worlds, and we can escape our natural limitations to an extent that animals could never do. They don't need much behavioral flexibility in their daily lives. They typically live a largely predictable life within the limits of their species' typical behavioral repertoire. So they eat, they sleep, they reproduce, but you wouldn't think of them, they wouldn't suddenly think that they want to go for the moon, for example, and make plans to realize that, like we do. But on the other hand, there are living conditions on the planet that might require cognitive flexibility and the ability to be spontaneous. It might be important for survival. For example, in harsh, complex, and unpredictable environments, it might pay off to be innovative and clever. And we are not the only species that are subject to this. But the big question is to what extent other species might have evolved complex cognitive abilities that allow them to cope with novel situations very quickly. I give you two particularly astonishing examples of such flexible behaviors in representatives of two of the largest brained avian families. I'm going to talk about New Caledonian crows, an island species that uses stick tools habitually for retrieving their food, and also about Goffin cockatoos, a particularly innovative and explorative parrot species living on the Tanimbar Islands. And I'm starting with one of the best studies to date showing that animals might be able to think about cause and effect to some extent and causally interfere to solve novel problems. Here we expose the birds to food out of reach presented on a platform inside of a transparent box, and there's a tube on top of the box. So please put yourselves in the perspective of the bird. It might seem very simple to you at first sight, but consider that they cannot lift or shake this box, and also we humans might comprehend from just looking at this box, seeing the hinges and the magnets, that the platform can be collapsed. But if you don't know that the platform can be collapsed, it doesn't make any sense to drop stones into this tube, which is obviously the solution to the problem. So we first established that none of our New Caledonian crows solved that problem without any experience of the mechanism. None of them did, and crows don't use stone tools habitually in the wild. But then we subjected them to two experimental groups that were allowed to learn certain aspects of this problem. So one group was trained to nudge stones from the rim into the tube right into its mouth, and so they were conditioned to carry out the correct behaviors, and they knew that stones were important and that they had to go into the mouth of the tube. Now she's complaining. Dohli, the other group, they only learned indirectly about just the mechanism of this task. They had to push the platform down directly with their beak through a shortened tube, but importantly, they never ever learned anything about stones being important. They were never reinforced for touching stones. So what do you think? Which of the two groups solved the problem? Not so surprisingly, the first group that had been trained to nudge stones into the tube succeeded, but their only transfer consisted in picking up stones and carrying to the mouth of the tube before dropping it. But also there were animals from the other group that succeeded, and they suddenly decided to use stones spontaneously as novel tools to solve this problem. And this is remarkable because they've never interacted with stones before. It actually shows that they were reasoning about the mechanistic structure of the problem and about physical forces, gravity and pressure, and were putting the two flexibly into relation until they came up with the right solution spontaneously. And I show you how this looked like in reality. This is first the training phase, where the bird learns to push down the platform with its beak, so it learns about the collapsibility. And next, it's exposed to the original test again, where there's a long tube on top of the box. And you can see that in the beginning, it's fairly annoyed that suddenly it can't reach the platform with its beaks any longer. But yes, Dohli is annoyed too. But then it clicks, and suddenly she uses a tool and with it extends its reach. Next, I'm going to talk to probably one of the most amazing innovative behaviors spontaneously shown by an animal reported to date, and that is by an Goffin cockatoo, a species that does not use tools in the wild. And this was a chance observation by my sister Elise Auersberg, who observed that Figaro, a cockatoo, was playing with a little stone, and at some stage he was inserting it through the mesh of the aviary, and it fell just outside of his reach. And then he tried for a few moments to retrieve it with his claws, but when this was not successful, he suddenly went away and came back with a little stick and then tried to fish for the toy out of his reach. After this happened, there was, of course, a follow-up study, and after this happened, he was immediately separated from his peers and tested under more controlled conditions. The bird was tested with a peanut, his favorite food, and it was just placed outside of the aviary behind the mesh. And to our big astonishment, the bird did not go and fetch the tool that we had provided, but instead, he started cutting out a wooden splinter out of the wooden beam of the aviary, step by step, and then used the splinter to... now she's bored, if you want to know. They start singing when they're bored. Then he used that splinter to fish for the food out of reach. But see for yourself, please. So you can see that it's pretty tedious to bite out the splinter, and it suggests that he really acted in a goal-directed manner. And you'll also see that it's not exactly easy to maneuver such a tool with a curved beak. We had to help him a little bit. But then it's not exactly easy to maneuver it, but if you look closely, he used his tongue to support the tool against his upper beak to have more control of the grip. We replicated this behavior, but he used several different methods and different materials flexibly, so we really had the impression that he had some kind of template in front of his inner eyes and was really producing the tools according to some plan. of course, we can't show that, and future research will have to study in more detail the cognitive processes that underlie such complex, innovative behavior. But he definitely shaped a novel tool out of a shapeless source material and to fulfill a novel need, and that meets the definition of real tool innovation. And it's maybe interesting for you to know that this is a behavior that tool innovations are developing very late in human ontogeny. While children readily start using tools at an early age, they only invent a tool readily when they're about 5 to 8 years of age. So this is surprising. So I hope that I could show to you that there's large-brained bird species have evolved capacities for complex thought processes that allow them to respond to novel situations flexibly and that allow them to solve novel problems. But this might be hard to swallow for some people that want to make a big distinction between animals and humans. But actually, I think there is a fundamental difference between us and animals, and that is that we are the only species that can fully foresee the consequences of our own actions. And as a consequence, we are also the only species that carries the full responsibility for our own actions. And therefore, my appeal to you is, if you want to be different, then show it and take responsibility for your actions for the sake of this planet and all species living on it. Thank you.